Definition of the derivative at x equals a. Objectives. By the end of this lesson, you should be able to list the three representations of a derivative, explain how secant lines are used to find a tangent line, state both difference quotient definition of the derivative, set up the limit required to find the derivative of f of x at x equals a, recognize when a limit represents a derivative and determine f of x at x equals a, and finally find the derivative of a linear function analytically and graphically. So this is all about derivatives. We are now entering one of the two main branches of calculus, differential calculus. So what is a derivative? When you hear the word derivative, I want three things to immediately come to mind. First, the derivative is a limit of a difference quotient. Second, the derivative represents instantaneous rate of change. Third, the derivative at a point is the slope of the tangent line at that point. Now I know they're all listed here as 1, 2, 3, but really they're all the same thing, right? All of these means the derivative and they're all equal to each other. So when I say derivative, I want you to have to know that it's the limit of a difference quotient, the instantaneous rate of change, and the slope of a tangent line. And that's actually the one we're going to focus on first, the slope of a tangent line. So what is the tangent line? If you remember back from geometry when we had a circle, the tangent line is the one that crosses the circle at one spot. We'd say it grazes the circle. We also had secant lines, so it's the tangent line. Secant lines are the ones that cross the circle at two spots. And we have the same thing here with function. And similarly, a tangent line to a point on a curve is a straight line that only touches the curve at a single point near the point and grazes that curve. What I mean by near the point? Well, near the point means, let's look at these two functions, identical functions right here. Right? If I'm trying to find the tangent to this point right there, this is a secant line, right? It goes through 2 points, so secant line. Over here we have a tangent line. Now, we say near the point because this graph goes on. For all we know, this graph looks something like this. And if we extend our line, it'll cross it again. But that doesn't really matter because all we care about is near the point. So we look at near the point. This thing only crosses it once. And it's also the way it crosses it, right? We want it to graze. That way we know it crosses it once it grazes it. If I did a line like this, that wouldn't count, right? That wouldn't count as a tangent line. It doesn't graze off the curve. It crosses through it. So this is not a tangent line. Right? You just want to barely hit it. So like that. That would be a tangent line. Or over here. That's a tangent line. Going through like that, not a tangent line. And this is important because the reason we're here is the slope of a tangent line is a derivative. That's the definition we're focused on right now. But the question is, how do you find the slope of a tangent line? Right, we know how to find slope. Slope is y2 minus y1 over x2 minus x1. But the thing about this is you need 2 points. Tangent line only has 1 point. So how do you find the slope of it? Well, we're actually going to use the slope of a secant line. And then we're going to use that to help us. If we look at the slope of a secant line, right, here's our secant line. The change in y, or f of x, is just f of x minus a. You just do y2 minus y1. The change in x is x minus a. Again, just x2 minus x1. The slope of secant line, also known as the difference quotient. We heard that word before, right? Slope of a secant line is a difference quotient. Remember, why is that? Because this is just normal slope, y2 minus y1 over x2 minus x1. That's all it is, right? You get 2 points. Secant line has 2 points. You find the slope of that secant line, and you get your normal slope. This is just a little fancier, fx minus fa over x minus a. But that's called a difference quotient. If you remember what our derivative was, one of the things was, it's a limit of a difference quotient. So the derivative is not the difference quotient. It's the limit of a difference quotient. That's going to come in handy real quick. Right, so how do we use secants to find our derivative, or to find tangent line? If you look at the graph right here, you can find the slope of this line, but that's not really the same slope as the one we want. Like this guy right here is a derivative. Actually, the slope of this line is a derivative, to be more correct, right? The derivative is not the line; it's the slope of that line. If you want to find this derivative, the slope of that line, I could use this to help approximate it. It's close. Right, the slope of this line might be 1, that might be like 2.5. What if I get a little closer, like over here? that's closer and is closer to my red line, but still on the red line. Then you can get a little closer, but it's still not the red line. But we can use that to help us, because you can never just do, once you get, the only way you can get a red line is if it's 1 point, and I can't find the slope of 1 point. So what we do instead is we get really close, or we use a limit as you get close to your point. So the limit of a difference quotient, and how do you find the slope? The slope is just the difference quotient. So if we take the limit of this guy, that's going to give us the derivative. That's kind of the idea, is that you take the slopes of all these things, you look at their limit, what's it going toward? It's going toward that tangent line right there. And that's kind of the idea. So in the pictures above, notice how Q moves closer to P, the distance between A and X is getting smaller, and the slope of a secant line looks more and more like the slope of that tangent line we are searching for. So that's kind of the idea. Let's formalize this. So we're going to formalize the definition of a derivative at a point using secant lines. So what's going on here is this. Here's my point A. So that means that the point right here is f of A, the y value. Let's go some h distance away. So we're going to go h distance away. So that makes this point right here is just A plus h. And it makes the y value up here f of A plus h. And then how will we find the slope of this secant line there? The way we find the slope of any line, right? y2 minus y1 over x2 minus x1. In this case, all right, so let's fill this out. So let's find x2. Remember, our x1 is A, our x2 is A plus h. So I'm going to have A plus h minus our x1, which is A. Now we need y2. Well, y2, remember, is right here, so our y2, so that's f of A plus b, minus our y1, which was just f of A. Now if you look at the denominator here, we can actually simplify that a little bit. This is just the same thing as just saying A plus h minus A, or just the same thing as saying h. So we have f of A plus b minus f of A over h. So this is another form, look at this one real nicer right here, of the difference quotient. Right, so now we have two versions of it, and they're both equal. You know both of them. We have the one we just found out, f of A plus h minus f of A over h, and we have the one we had before, which is just like a fancier way of writing slope, which was f of x minus f of A over x minus A. Remember, that's really just the slope equation. This is like a simplified version of that. Now let's talk about the derivative. Remember, this is just a difference quotient, not the derivative. The derivative is the limit of the difference quotient. Very important. Right? We're going to take the limit of that, like we talked about earlier. If you just take the difference quotient, just a slope. But I want the tangent line. So with a tangent line, so you have to take all difference quotients. You have to take the limit of all them all. And that gives you the slope of the tangent line, which is a derivative. Right? So this is just a difference quotient. And when you take the limit of them, you get the derivative, or the slope of a tangent line, or it's the tangent rate of change, right? They're all equivalent. So let's look at it more formally. Derivative at x equals a, the derivative of a function f is valued at x equals a, is the limit of the difference quotient. And this has some notation. This right here means derivative at a. So derivative at x equals a is this notation. It's a little prime symbol we put for derivative at a certain value. And that is this equation, provided the limit exists. When the limit does exist, we say this is differentiable. So when you could take a derivative, it's called differentiable at x equals a. Alternate form of this derivative at x equals a is given by this thing. So we have these two forms, right? We have this one and this one. Two forms of the limits of a difference quotient. Now let's do an example. Example. Find derivative f of x equals x squared at x equals 3. Now, so we're going to find this derivative of x squared at x equals 3. Let me show you the different ways that they could ask you that question. They could also say, find the slope of a tangent line to the function f of x at x equals 2, f of x equals x squared at x equals 3. Or they could say, given f of x equals x squared, they could use notation, and they could write find f prime of 3. So there's three ways to ask the same question, right? They can say just find the derivative of x squared at x equals 3. They could say find the slope of the tangent line to the function f of x equals x squared at x equals 3. Or you could say, given this x squared, find f prime of 3. So let's quickly talk about what we're actually doing here. So I'm going to draw a graph real quick. Let me just go get a little space. And now I'm going to draw a graph for x squared. So let's see if it's a parabola, so it's going to kind of like this. All right, just to give an idea. And we want it x3, so over here. We're trying to find the slope of the tangent line at x equals 3. So right around there. So let me draw a tangent line to that graph. Remember, tangent lines could only graze it, so something to this effect. Not perfect, but whatever. We're trying to find the slope of that tan line. That line right there, right? So we want to find the slope of the tangent line. Let's do it by using our two formulas, right? There are limits of the difference quotients. We'll do this one first. So I'll have to plug it in. So we want to find it at x equals 3. So we're going to do f prime of 3 equals the limit as h approaches 0 of f of a plus h minus f of a. So f of a plus h just means we're going to plug a plus h into our x squared. Now, remember what our a is though. It's 3. So let's do it right here. I have to plug in 3 plus h into my function x squared. So remember, x squared is my function, so it's just this, right? F of x in general, it's a placeholder. It's whatever this thing happens to be, you plug it in there. So most of the time we just use x as a placeholder. In this case, it's 3 plus h is what I'm plugging in. So I'm going to have 3 plus h squared. So it goes here, 3 plus h squared. Right, because 3 is my a, and it goes there. Next we got to do the minus f of a. We got to do this part. Right? So let's put negative all over h. Let's talk about what f of a is. So remember, a is 3, so we're going to plug 3 into our function. That's going to get us 3 squared. Now all we got to do is simplify this, right? Some algebra. Let's start off with this 3 plus h first. Don't give me 9 plus h squared. Remember, the way you do this is 3 plus h squared. It's not squaring each thing because there's a plus sign. You can't do that. What you do is you multiply it by itself. 3 plus h times 3 plus h. If you do that correctly, you should get 9 plus 6h plus h squared. So we're going to have 9 plus 6h plus h squared. Everything else is still here. We still have an h. We still have the limit as h approaches 0. Remember, you can't get rid of that until we sub it in. And we still have minus, in this case, 9. Just because the next part is my favorite part. Let's simplify this a little bit. 9 and the 9's cancel. So I just have the limit as h approaches 0 of 6h plus h squared over h. Now this is just a limit problem now. That's all it is, right? We want to sub in 0. But what happens if we do it right now? We get 0 plus 0 over 0. And actually, that was the same thing up here. This was just the limit problem. Right? If I plugged in 0, I would have got 3 squared minus 3 squared, which is 0, all over 0. Right? Indeterminate form, we have to do more work. So, we simplified it. And I got to this. And it's the same idea. Still get 0 over 0. So, we simplify it. Notice the top here. They both have an h. So, we can factor out an h. So to put the limit, these cancel out, and I get the limit as h approaches 0 of 6 plus h. I could finally just sub it in, and I get 6 as my answer. So the slope of the tangent line, I always do that, is 6. Slope of the tangent line is 6. So if we go back to our graph right here, slope of that line right there is 6. Or the derivative at 3 is 6. So we did it one way. Let's do it the other way. Let's use the other definition of derivative, right? Limit of difference quotient. This actual one, I think it goes by a little easier. So same idea, we have to fill stuff out. Now, f of x is just x squared, right? That is our function, x squared. Notice that there's no variables inside, it's just the function. We're going to do f of a. Now, I should say this earlier, right? We're still doing f prime of 3. So our a is 3. So this is minus f of 3. And the same thing down here. X, and it's just x, a is 3. So let me just rewrite it. So this is the limit as x approaches 3. Now notice how that is different than the one we did earlier. This one has limit as you approach your variable we're looking for your a. Over here it's always 0. And we're doing the first version of it. In this version, it's whatever your a happens to be. You're trying to get these two things close to each other. You're trying to plug in 3 so it gets very close to 3. All over x squared minus f of 3, all over x minus 3. Remember, all f of 3 is plug 3 into the equation. So this is just 3 squared. We're plugging into our equation. So I have a limit as x approaches 3 of x squared minus 9 over x minus 3. Now keep in mind, this is just an limit equation, right? That's all it is. We have a limit problem now. If I try plug in 3, I'm going to get 9 minus 9 is 0 over 3 minus 3 is 0. So it's an indeterminate form, which means we got to do more work. So in this case, we're going to factor x minus 3, x plus 3, 2 squares, all over x minus 3. These do cancel out, and we get the limit as x approaches 3 of x plus 3. And now we can sub it in and just get 6. So either way, we get the same answer. And that's using the limit definition of a derivative to find the derivative. Okay, our next example. Now we're told the following limits represent derivatives of f of x at some x equals a. Find f of x and x equals a. So it's kind of going backwards. We're saying, hey, they want you to notice this is a derivative, right? It's a limit, it is, but it's a derivative. It's a fancy way of writing derivative. So they want to know what these two things are. What is f of x and what is our a, essentially. So looking at this formula here, we got to think back to the formulas we just found out about, right? Our derivative formulas, that is limit of a difference quotient. So we have this form of it, f of a plus h minus f of a, all over h. And the other version, limit as h approaches 0, of f of x minus f of a over x minus a. Right? And again, what we're trying to do is find f of x, like what is our original function, and a, where are we finding it at? Or what value are we looking for? So if you look at these first two here, they kind of match the top one right here, right? This top version of limit of a difference quotient, top version of a derivative. Now a is probably the easiest thing to find. It's always next to the h. So our a right here is this 2. Easy enough. Right? If I was doing this one, I'll tell you right now, it's 16, right? It's the thing next to the h. Now the function is a little tougher. All I ever do is just kind of wipe away this 2 plus h. This is our function. Just ignore the 2 plus h. This is like our x. So it's x cubed. That's our function, right? Because this is what you plug in for. This is where x would be. So I just always erase it out of my head and say, okay, it's x cubed. That's our function. And you can check by doing this one. If I plug this into there, do I get that value? 2 cubed is 8. So yeah, that's the way it works. So same thing with the next one here. Right? The whole idea of this problem is to go, okay, this is a limit of a difference quotient. This is a derivative. What's my function? And what's my a? My function and my a. I always think a is the easiest. A is just the thing next to your h. So in this case it would be 16. And then what's my function? It's what, if you just take all this away, the h plus the a, it is square root of x. And again, you can double check by looking at this right here. If I plug this in there, do I get that value? 16, square root of 16 is 4, so yes, it checks out. And that's all we're doing here. We're just going backwards. Now let's look at using the other formula. Let me write the other formula of a limit of difference quotient, or the other derivative formula. As x approaches a, f of x minus f of a, all over x minus a. And I think I forgot to make it go to a over here. So let's double check. Anyway, I think this one's actually a lot easier than the other way, because we're looking for f of x and we're looking for a, and they're actually already in the formula, right? Here's our a, here's our f of x. So if you notice, it's this type of problem where I just want you to figure out what f of x and a is. If it's in this form, it's actually a lot easier. A should be the thing right here. F of x is the value. Is the function. If you notice, you can double check it also, right? Right here is f of a. So if I plug my a into f of x, I should get this value. If I plug 2 into my equation, do I get e squared? Yes, I do. That's all it is. So in this form, it's actually easier. The first thing here is a function. Your a is down there, right? Where in the last one, your f of x, so you have to kind of like ignore this part. It's put it next there instead of the 2 plus h, and your a is always the number next to your h. And then one right here, same question. What is f of x? What is a? A is the thing next to the f of x, so pi over 6. Another way, a is also this guy, so either way you want to look at it, f of x is always a function by itself. And that's that one. That's going backwards. That's going, hey, here's a difference quotient, here's a limit difference quotient, figure out f of x and a are. Right? So these are fairly easy, but what is required, you have to know both forms of the limit definition of a derivative. Right? If you know these forms, it's really easy. If you don't, it's going to be impossible. Okay, let's go to our next thing we're going to talk about. Theorem. If f of x equals mx plus b is a linear function, then f prime of a is m for all a. So let's just think about that for a second, right? We have a picture here. They're saying, hey, if you have a linear function, mx plus b, that the derivative is always a slope. That's what I'm right here. Right? The derivative of a linear function is always the slope of the line. Why? Well, think about it logically, right? I have this line here, this graph here. Let me change the color actually to better. If I want to find the slope of the tangent line, which is what a derivative is, well, how do you draw a tangent line to this thing? It's the same line, right? This touches it the whole way. So the slope of a tangent line is equal to just the slope of a line when it's linear. So they're the same thing. So the slope of a tangent line is the same thing as the slope of a line. That's why it works. So for an example, let's say I gave you f of x equals 3x plus 2. If I asked you what f prime of 5 was, again, nothing, it doesn't really matter. This is a linear line. The derivative is 3. I can ask you what f prime of x is. It's just going to be the slope, 3. No matter what I plug in there, the derivative is always going to be 3. It's the slope of the tan line. Right? So that's the idea, right? I could give you f of x equals negative 2x plus 3. The derivative of any number, say triangle, to that function has to be the slope every single time. Let's talk about a little corollary to this. If f of x equals b is a constant function, then the derivative is always 0 for all a. So if a constant function is always 0. Why? Well, think about it again. How do you draw a constant function like this? Right? If I said f of x equals 4, the way you draw f of x equals 4 is like y equals 4. 1, 2, 3, 4. It's a straight line across. What's the tangent line to this? Well, just the same line. What's the slope of a straight line? 0. So anytime you take a derivative of a constant, you're going to get 0 because this is a straight line, and the derivative of a straight line is 0, and that's why. So I can say, hey, what's the derivative? If I give you f of x equals 5, the derivative of f of x is going to be 0. Right? The derivative of a constant is always 0. Now let's use that idea to do some problems like this. So let's find some derivatives. Let's find f prime of negative 2. Given this is f. Let's find f prime of 0. And let's find f prime of 5. Now the way we're going to do this, since we have a graph, is we're going to do it by find the slope of a tangent line. Right? We're going to use that version of the definition. Remember, there's 3 ways to find a derivative, right? We have 3 definitions for it. Slope of a tangent line, instantaneous rate of change, and limit of a difference quotient. Right? In this case, since we have a graph, we're going to use the slope of a tangent line to find it. So let's talk about f prime of negative 2. So here's negative 2. all we gotta do is find the slope of that line, right? Because the tangent line is the same thing, so we're gonna find the slope of the line, just like we do in Algebra 1. Take 2 points, rise over run, 1 and 1, so my slope there is 1. Now let's talk about f prime is 0. So here is 0. Now look, that's an interesting one. How does a tan line look on that? Right, it was a curve. The way you draw a tan line to a curve is you hit it a straight line. That's what's going on right here. Straight line. And what's the slope of a straight line? 0. So anytime you have a curve, it's a very big result. If I say what's the derivative of these curves here, they're always going to be 0. That's going to become super important later on. The next one, let's take derivative at 5. Here's 5. And we're trying to find the slope of the tangent line. Well, the tangent line is just this line there. The slope of a straight line is 0. Right, so that's how you find the slope of a derivative given a graph. You just find the slope of those tangent lines. Let's do one more, then we can get out of here. Let's do f prime of -4, f prime of 1, and f prime of 4 again. F prime of -4, so now you go to -4. So you gotta find remember, now that's a linear line, right? So the tangent line is the exact same thing. Let's find the slope of that big old line there. We use Algebra 1 skills. I want to find a slope. It's like rise over run. But right there, it looks like it is at 6, and we went down to -6, and I went over 6. So my slope of that tan line is -6 over 6, or -1. F prime of 1, here is 1. Go to the graph. Derivative is the slope of the tan line, so it's just that line. We gotta find the slope of that line. Algebra 1 skills again. Right, this is 2 and this is 2. So my slope is just 2 over 2, which is 1. And then finally, the last one for today. F prime is 0. Here is 0. Right, slope of the tan line is just that line right there. And your slope of a straight line is always 0. And that's the idea. Before I go, look, quick recap. Remember, I want you to remember 3 definitions of derivative. Right, 1, slope of a tan line. And I know it wasn't 1 before, but they're all equal. That's one that came to my mind first right now. 2, instantaneous rate of change. We'll work more on those later. Those have to do with like application problems. And then 3, limit of difference quotient. Now remember, not the difference quotient itself, the limit of difference quotient. Right? The difference quotient, just by itself, is the slope of a secant line. Just normal slope. Right? We do the fancy this way. That's just normal slope. We're trying to find the slope of a secant line. Right? The limit of those guys gets you the derivatives. Those are my 3 definitions of derivative. Right? Slope of a tangent line is instantaneous rate of change, and the limit of a difference quotient. Don't forget, difference quotient is this guy. It's the slope of a secant line. But the limit is a derivative. And also, right, the different ways to do that. There's 2 ways, right? The limit as x approaches 0 of f of a plus h minus f of all over h. Or you could do the limit as x approaches a of f of x minus f of a all over x minus a. Right? Those are the big ideas from this lesson.